Yes, thank you very much for the invitation to speak in your new series, new seminar series, Geometry and Tacos. So the aim of my talk is modest. I will just discuss three families of K3 surfaces and compare their properties. So we could start with a K3 surface S. And the Fermat quartic in P3 given by the equation, by the Fermat equation will be one prominent example. Then I want to deform this K3 surface in a one-dimensional family, and I want to study the propagation of certain properties. Eventually, I'd like to use this to understand a phenomenon that I observed last year, how certain algebraic cycles and arithmetic properties propagate along the twistor family, and that's why I compare the twistor family with the dwarf pencil and the Brouwer family. Okay, before I really dive into the discussion of these three families, let me recall what you need to know about K3 surfaces in order to follow this talk. So just recall that a K3 surface is a compact complex surface S, such that we want it to be connected. We want it to be simply connected, and we want its sheaf of holomorphic two forms to be trivial. Okay, it is known, it's not easy, but it's known that S then is actually Kähler, and in particular we can look at the Hodge decomposition of its second cohomology. There are no surprises here. So there are three parts, 2, 0, 1, 1, and 0, 2, and the 2, 0 part and the 2, 0, and 0, 2 are complex conjugate to each other, and the 2, 0 part is the space of global sections of the canonical bundle, and since this is trivial, it is generated by a trivializing section, and this trivializing section will be thought of as a symplectic, holomorphic symplectic form. And then the 0, 2 part is spanned by its complex conjugate. The intersection form on the second cohomology is well known. It is a unimodular form with 3 positive eigenvalues and 19 negative, so the signature is 319, and the positive definite part can be chosen to be the real vector space, the real plane underlying the 0, 2 and the 2, 0 part, and then you just pick one Kähler class omega, and the intersection form will be positive definite on this one, and then as a consequence it will be negative definite on the orthogonal complement of the Kähler class in the real 1, 1 part of S. The Picard group is nothing but the Néron-Severi group, and this in turn is just the 1, 1 part of the integral cohomology. Its rank, so the Picard number, will be denoted by rho. The signature of the Picard in the intersection form restricted to the Néron-Severi letters is of course then 1 rho minus 1 whenever S is a projective K3 surface. We'll also need the transcendental part, which is just the orthogonal complement of the Néron-Severi letters. It can also be described as the smallest primitive Hodge substructure, such that the 2-0 part of S is actually contained in the complexification of T. We will also need the endomorphism field, so the endomorphism ring of all endomorphisms of the transcendental lattice and Q coefficients. So this is the ring of all Q linear maps, which are also compatible with the Hodge structure. So that means, for instance, the 2-0 part, phi of the 2-0 part is nothing but is contained in the 2-0 part on the other side. The same for the 1-1 part and the 0-2 part. And an observation by Sarshin coming from P and varieties is that this is a field, and that's why we called it K. So is a field which can be naturally embedded into C by mapping an endomorphism phi to some lambda, where the lambda is given by the condition that phi of sigma is lambda times sigma. Remember, sigma spans the 2-0 part. Phi of sigma for an Hodge endomorphism will be again the 2-0 class, so it will be a multiple of this sigma. So we write it as lambda minus sigma, and this is the lambda. And this turns out to be an injection of the endomorphism ring, which thus becomes a field. And he showed more, namely, he showed that there are two cases. The first one is that this field is actually a subfield of the reals, so it's actually totally real field, and we say, this has real multiplication. And the second case is it is not a totally real field, but it has a totally real field, contains a totally real field, such that K is only of degree 2 over it, and in fact it's a totally imaginary quadratic field extension of this one. So that means lambda is a real negative real number. And the second condition occurs if and only if there exists an endomorphism that's not plus or minus the identity, and which is also an isometry. And this case is called the complex multiplication case. So we have these two just characterizing characterized by the property of their field. Sometimes it's we need a slightly stronger notion of complex multiplication, but let me not go into this. There's also a geometric way of seeing this endomorphism field, namely, by definition, the endomorphism of a vector space, of course, the same as the tensor plot of the dual and the vector space. So I'm doing this for T here, and then the condition that's a Hodge endomorphism means that in this tensor product of these two Hodge structures, we're looking at a 2-2 class, and by Poincare duality, T is of course isomorphic to T dual, and we're looking at the 2-2 class and the tensor product of T tensor T, and this is the interesting subspace of all 2-2 classes on the product of S with itself by Kühnert formula. And the totally real subfield K0 then corresponds to the symmetric classes, so those classes that are invariant under swapping the two factors. Okay, I think this is all you need to know from the theory of K3 surfaces, and I can dive into the first family right away. So we start with the Fermat quartic. MP3, and now deform the equation by one monomial, where we put in a factor in front of it, and that's still a quartic equation, and we get quartic surfaces in P3, and in fact we get a family S over A1. So A1 parameterizes the parameter T. So it is of course nothing but C, but I write A1 to stress the algebraic nature of this construction. Okay, we know that not all fibers are actually smooth. The fiber is smooth if and only if T is not a fourth root of unity. If it is, so if the fiber is singular, then it has just 16 ordinary double points, and the minimal resolution is then a Kummer surface. Is a Kummer surface. The fact that we don't really have a smooth family of K3 surfaces is not, that's a family of K3 surfaces, smooth only over the complement of these 4 points. But it's really not important for what I have to say. In any case, you can always take a degree 2 to 1 cover of A1 and pull back the family. This then becomes a singular threefold, and there is a small resolution of this, a small blow up, such that this then is a family of a smooth family of K3 surfaces, smooth family of K3s. So let me not worry about the singularities for mildly singular fibers at all. Let's look at the center fiber. The center fiber is the femar quartic, and it has a rather large Néron-Severi group. So the rho of S was the rank of the Néron-Severi group, and this is actually 20. So this is the maximum possible number, simply for the fact that there are many lines contained in S. For instance, you could look at a line like this, where zeta to the fourth is -1, and you can write many more lines, and this forces the Picard rank to be 20. Consequently, the transcendental lattice, which was the orthogonal complement, then has to be of rank 2, and its intersection form can be computed. It's rather easy. It's of this diagonal form. It turns out that, so we know the Picard number now, but it also turns out S has complex multiplication. And in this case, its endomorphism field is simply Q joint I. Okay. For all the other fibers of the Dwork pencil, sometimes I should say, some people call this the Fermat pencil. It also comes up in mirror symmetry, and some quotient of the Fermat pencil will then be called the Dwork pencil. But let me stick to the name Dwork. It turns out that for all T, the Picard number of the fiber is at least 19. Okay. And in fact, there exists a line bundle, which I call LD, so D for Dwork, in the Néron-Severi of the Fermat quartic, which has negative square, and it turns out it has square -4, such that that the orthogonal complement of it, so this sits in as the orthogonal complement in the Néron-Severi lattice of S, sits actually in the Néron-Severi lattice for all T, and in fact for T very general, it is the Néron-Severi lattice of the fiber. Okay. Oops. Now, what I want to understand is for which other t do I have a maximal Picard number and complex multiplication. Okay, so for this I define the two loci, Noether-Lefschetz and complex multiplication, just by saying I want to, should be the set of all t's where the fiber has a Pk rank 20, and this is the set of all t's where the fiber St has complex multiplication. So in this case, it means that this endomorphism field is of rank 2, as of the degree 2 over C. So Hodge theory, this is standard Hodge theory, tells us that the Noether-Lefschetz locus in C, so C as the basis of A1, is in fact countable and dense. Okay. On the other side, if T is not a point for which the fiber has complex multiplication, so T not contained in CM, then this is the case if and only if the endomorphism field is just Q, and this essentially means that there are no interesting cycles, interesting Hodge classes in on the product. Okay. So this fact that the Noether-Lefschetz set is countable and dense reminds one of for instance the set of all algebraic numbers. So this is also countable and dense, and there is in fact a relation between the two, but not as nice as one would like it to be. Namely, if you have a point in the Noether-Lefschetz set, then this T is in fact an algebraic number. But the other direction does not hold. In fact, we know the almost true case of a result by Orr and Skorobogatov that the set of points in the Noether-Lefschetz locus that are actually rational numbers, that's a finite set. So in particular, most of the rational numbers do not give Fermat, do not give a quartic K-thesis with maximal Picard number. The conclusion in this case is the following. This is all rather well known. For the Dwork family, these two sets, write this here, these two sets, Noether-Lefschetz and complex multiplication, are the same sets in A1, so it's just C. So in particular, they're both countable and dense. So this is the kind of statement I'm after. Okay, let's go to the twistor family. So again, I look at the K-thesis of this S, and I pick any Kähler class. Kähler class on S. And then by Calabi-Yau, I know there exists a unique Kähler form or Kähler metric G, such that so on the complex manifold, which we think of S, which we think of a differential manifold M plus a complex structure I, such that the Kähler form, which I got out of the Kähler metric, represents alpha, and that's the important condition. Its square, which is a 4 form now, is essentially up to a factor sigma times sigma bar. Remember, the sigma here was the generator one generator of the space of two forms. In fact, there's a the whole structure is hyperkähler, and that means there exist complex structures ijk, so I is the given one, and k can be written as ij or it's minus ji, so ijk satisfy the usual conditions, and these are all complex structures, and G is scalar with respect to all of them, I, J, K, and we can find the Kähler form of G with respect to J and K as real and imaginary part of the holomorphic two form with respect to the complex structure I. In fact, for all T triples A, B, C in the sphere, the linear combination of I, J, and K defines a complex structure, and what I get is a smooth family of K3 surfaces S over P1, so the P1 here I identify with S2. So the S is really nothing but the differential manifold M times P1, endowed with a complex structure I, such that I restricted to M times T is nothing but the complex structure IT I just defined for you. Okay, so this is the S is a complex manifold, that's a complex threefold, and the pi is holomorphic. Okay, and for the fibers ST, which are given by M endowed with a complex structure IT, the holomorphic two form for this K3 surface then is always a linear combination of the original sigma conjugate, and the Kähler form omega I. Okay, we want to be slightly more algebraic and start with an algebraic and with an ample class of some line bundle LT. So the T here is for twistor, and the LT is ample, otherwise it wouldn't be a Kähler class. Ample, it is in fact its first Chern class is in fact the real part of the holomorphic two form with respect to the structure sigma k. In particular, it's contained in has no part in the 1-1, no contribution to the 1-1 part with respect on the fiber SK. Okay, so in particular, so it's not 1-1, and that means the LT does not stay holomorphic as a line bundle on all the fibers. LT does not stay holomorphic. Okay, so let's look at the orthogonal complement of LT. Then if you take a line bundle in here, let's say L prime, then the L prime is certainly, because it's a line bundle on, this should be on the original K3 surface. It's certain, since it's a holomorphic line bundle, it's certainly orthogonal to sigma, it's orthogonal to sigma bar, and by assumption also orthogonal to LT, and that means L prime is really 1-1 on all fibers. Okay, so that means we do have an embedding of LT in the Néron-Severi of any fiber, in particular, and maybe in particular the any fiber has at least Picard number rho s minus 1. Sorry, I was just looking whether I introduced all the notations in the dwarf family case. I did, and for very general T, this is in fact inequality. Okay. Note that in particular, this proves that most fibers are not projective. So what we have here is a smooth family of K3 surfaces, but not projective. In fact, S is not even Kähler. Okay, and now we again ask the same question as for the dwarf pencil. I would like to know for which T do I have the maximal number? In this case, I just want it to be rho of S, or at least rho of S. And I would like to know when has ST complex multiplication. And this question only makes sense if we really assume that that S, the original K3 surface, has complex multiplication, so has interesting cycles on the product. As before, we introduce the corresponding sets, the Noether-Lefschetz and the complex multiplication set. So the Noether-Lefschetz is the set of all T's in P1 such that ST is projective, which right away implies that the Picard number is at least rho of S. And the CM set is the set of all T's such that ST is projective and has complex multiplication. Okay. Again, Hodge theory tells us that the Noether-Lefschetz set is dense uncountable. And there's a curious observation saying that a priori it could happen that the Picard number of a fiber not only jumps to rho of S, so the Picard number of the original K3 surface, but jumps higher than that. So the set of all those fibers where the Picard number is even bigger than S turns out to be contained in a sphere in the equator. So this is the equator here. So the original K3 surface S, which was MI with a holomorphic 2 from sigma, was here, and then there's the equator, which is in fact the set of all T, such that C1 of L is contained in the real span of just in the span of in the span of sigma for the complex structure T and sigma bar. So that turns out to be an S1. And what I proved last year is the following. So assume S has complex multiplication, and this is the twistor space, twistor family associated with an ample line bundle. I call it again LT. Ample. Then the Noether-Lefschetz locus and the CM locus are the same, at least away from the equator S1. And of course, they are both countable and dense. And a second curious property is that for all points t in the neutral left-shift locus away from the equator, I can compare the endomorphism fields of the fiber ST and of the original K3 surface, and it turns out the endomorphism field might not be the same, in general they will not be, but they're totally real fields. So those Hodge class on the product S times S that are symmetric under swapping the factors, they are isomorphic. So remember, this is in H2 to ST, ST, and this is in H2 to S times S, Q, everything with Q coefficients. The exact relation between these two is what I would like to understand. Okay, so this is the second family. I can now come to the next one. That's the Brouwer family. So again, S it can be, first of all, any K3 surface, and then one defines the Brouwer group. I'm just defining the Brouwer group without really interpreting this in terms of Azumaya algebras as the torsion part of the second cohomology of O star. So that's a group, and I can look at its torsion part. I can also, at least in the algebraic situation, can also define this as the eta cohomology of S with coefficients in the multiplicative group. There's a bigger group, so why only taking torsion classes in this cohomology? I could just take the full cohomology, and this is we call the analytic Brouwer group. Okay. The exponential sequence allows us to describe this group. The exponential sequence gives us this exact sequence. Okay, so that's subjective here, and up to finite group, we find that the Brouwer group is the analytic Brouwer group is the quotient of a one-dimensional vector space. Oops, this one here. By the transcendental lattice, and the algebraic Brouwer group, Brouwer of S, is then just the quotient of the rational transcendental lattice by the integral one. Okay, so in particular here we see this is roughly C divided by Z to the power 22 minus rho, and this one here is Q modulo Z to the power 22 minus rho. Now that's just the definition of the Brouwer group. It becomes more geometric if one looks at an elliptic K3 surface with a section. Okay, then there's what's called the Tetrahedra Group, and again it comes in an algebraic and an analytic flavor. Let me this time start with the algebraic definition. This is just a set of all elliptic K3 surfaces over P1. Oops. Elliptic K3 surface, such that the relative Jacobian of S prime over P1 is in fact isomorphic to the original elliptic K3 surface S. So this happens over P1, and there's a subgroup, the algebraic Tetrahedra group, with the same definition, except that this time I also want the K3 surface to be projective. Okay, here, so this relative Jacobian, maybe shift this here. So the relative Jacobian can be interpreted as a moduli space of rank 1 sheaves on the fibers. So for if the fiber S prime lambda is smooth, then this is really the fiber of this of the relative Jacobian really is just pig 0. So the Jacobian of the fiber, and the condition here says that these relative Jacobians of the fibers become isomorphic, put in a family, become isomorphic to the original K3 surface S. Okay, and then there's a theorem that says there is in fact natural isomorphism between the analytic Tetrahedra Group and the analytic Brouwer group, which induces an isomorphism between the algebraic counterparts. So this is the proof is a Comanche computation, but one can give it some geometric interpretation. Namely, suppose you look at the Brouwer class alpha here, and I'll tell you what's the relation to the corresponding elliptic K3 surface on the other side. You see what I told you here. What I told you here about the fibers of the relative Jacobian. This means there is a Poincare bundle on the fiber, on the product of the fiber of S prime with the Jacobian, the fiber of lambda, and this is of course just S, the fiber of S, if we are looking at an elliptic K3 surface in the Tetrahedra group, and the obstruction to glue the P lambda to a universal bundle P or universal sheaf over the product of these elliptic K3 surfaces over S is a class alpha in the Brouwer group of S. Okay, so now the interesting observation is that this can all be put in a family. Remember, the Brouwer group was the quotient of a one-dimensional vector space, the analytic Brouwer group. And in fact, if I look at the Brouwer class associated with an element in this complex line, then one can indeed construct a family of smooth K3 surfaces with the property that the fiber over a point T and C is in fact isomorphic to the K3 surface, the elliptic K3 surface that corresponds under the isomorphism of the analytic Tetrahedra group and the analytic with the analytic Brouwer group to the class alpha T. Right. Okay. So and as similar to what we had before, there is we can try to understand the Tetrahedra group of the generic fiber of this. There's again a line bundle, which I call LB, so B for Brouwer, which is nothing but the fiber class of the original elliptic vibration. And it turns out, so I can look at its orthogonal complement. This time, it's a little bit more complicated because this is a line bundle of square 0. So in particular, LB itself is an element in its orthogonal complement. But it turns out that again, the orthogonal complement sits in the Tetrahedra group of any fiber. So in particular, we have that every fiber has a Picard number at least rho of S minus 1. This here is a degenerate, so it's a non-definite lattice. So it has signature. There's no positive eigenvalue anymore. It has rho minus 1 negative eigenvalues and 1 isotropic class. So this corresponds to LB. And then the same question as before, for which T do I have the original Picard number, and for which T is the fiber, has the fiber complex multiplication. And of course, this question again makes only sense that when the original K3 surface has complex multiplication. And we define again the Noether-Lefschetz locus and the complex multiplication locus, and this is the set of all C's, of all T's in C, such that ST is projective, and in particular, this then implies that its Picard number is at least rho of S, and the CM set is the set of all T's, such that ST is projective and has complex multiplication. Okay, and in this case, without going into any details, we have something that by now probably looks familiar to you, namely the Noether-Lefschetz locus is in fact the same as the CM locus. It's a countable and dense set. And if I map to the analytic Brouwer group of my original K3 surface, which was this wild group, then the Noether-Lefschetz locus or the CM locus is nothing but the pre-image of the algebraic Brouwer group. Also, for any point in the Noether-Lefschetz locus, I can compare the endomorphism fields of the fiber with the endomorphism field of the original K3 surface, and they turn out to be the same. So there's, I don't have to pass the real multiplication fields, they're just the same. And in fact, so again, these endomorphism fields are natural subspaces of the space of Hodge classes on the square of the K3 surface. And in this case, we do understand the relation between the Hodge classes. I don't have time to explain this, but here some of the situation is well understood. Okay, so I've discussed these three families. I've given you some facts that are well known, and then I also gave you this slightly surprising thing about the twistor space. And let's maybe, to summarize this, let me compare the three situations once more. Okay, so let me recall the Dwork. The Dwork pencil was a family of K3 surfaces over A1 with 4 mildly singular fibers. Let's not discuss this. And we started with a K3 with a Fermat quartic that came with a line bundle LD of square -4. Okay, and this is a projective family. It has, if I not really take out the singular fibers, it has all paths to this degree 2 cover. It has non-trivial monodromy. The Noether-Lefschetz locus is the same as the CM locus, and all the totally real subfields of the endomorphism fields are the same which in this case is a little silly. So this is for all t in the neutral Lefschetz. Oops. This is for all t in the neutral Lefschetz locus, which is a little silly in this case because it's simply just Q. Okay. Now, the twistor family was again a one-dimensional family of K3 over P1. This worked for every K3 surface with an ample line bundle LT. I could apply this to the Fermat quadric, and then the line bundle, the distinct line bundle I would take would be the hyperplane line bundle O1, and its square has of course 4. This family is not projective. It has trivial monodromy. In fact, the S is as a manifold is just M times P1. Again, the neutral Lefschetz locus is the same as the complex multiplication locus. And whenever I'm over the neutral Lefschetz locus, the total real fields of the fibers is the same as the one of the original S. I should have assumed that S has complex multiplication, and this works for all t in the neutral Lefschetz locus away from the equator. And finally, we have the Brauer family. Here we start with an elliptic K3 surface S over P1. You can take the Fermat quadric if you want, and then you take as a line bundle LB the class of the fiber. And again, this is not a projective family. Maybe I should write here. This is a family S over C. So this is not projective. It has certainly trivial monodromy. Its neutral Lefschetz locus is the same as the complex multiplication locus. And in this case, I know that the endomorphism fields are the same for all t in the neutral Lefschetz locus. Okay, so the last thing I want to do in this talk is to view this situation from the perspective of periods, and then we will see that there's not just this analogy between these three families, but in terms of periods, there are really 3 examples of a similar construction. And it seems instructive somehow to write these 3 descriptions on the level of periods, one next to the other. Okay, so that will be last part. So let me first recall a few facts concerning period domains. So I start with the lattice lambda, which is just the lattice of any K3 surface Z. We know its signature is 319. And then we look at the period domain, so D, so that's the period domain, D in Q in the projective space. I get from the complexification of the lattice, so which is a 21-dimensional projective space. This here is just the quadric defined by the intersection form. So that's a smooth quadric in this P21. The D here is an open subset of it. So the same condition, so it has to be on the quadric, and I add a real condition, namely that X, the intersection product of X and complex conjugate X is actually positive. And then we know that there exists a universal family of marked K3 surfaces S over this period domain and period domain D. If I divide out D by the natural action of the orthogonal group of the lattice lambda, then this is really the set of isomorphism classes of all K3 surfaces. Okay, and this is really by, if I have S together with the marking, so an isometry of the second cohomology with lambda, then I associate to it the 2, 0, the image of the 2, 0 part under phi, which then is a point in the quadric, and in fact it's a point in the period domain. Okay, so now I want to use this general picture to describe the three families, Dwork, Twister, and Brouwer, and I really now do this just for the Fermat quartic. So S again, the Fermat quartic. Remember the Néron-Severi is of rank 20. Its transcendental lattice is of rank 2. So this is rank 20. Oops, rank 20. This is rank 2, and the direct sum is almost the full cohomology up to finite index. And I have 3 line bundles. I have the Dwork line bundle, the Twister line bundle, and the Brouwer line bundle. They're distinguished by their squares. The Dwork line bundle has negative square, namely -4. The Twister line bundle has a square 4, and the Dwork line bundle, the Brouwer line bundle has square 0. Okay. Also, the transcendental lattice is rank 2, and I told you already that its intersection form is of diagonal shape, and the important thing for us is if I complexify this lattice, then is of course generated by the holomorphic 2 form and its complex conjugate. So that's 2, 0 here, and this is 0, 2. Okay, let's see. So for the Dwork pencil, we make the lattice T, the transcendental lattice T, bigger by adding the Dwork line bundle, LT, and I'm only interested really in the real picture, so I tensor with the reals right away. So this, of course, I can view as a real 3-space subspace of the lattice lambda tensored with R, and if I look at its intersection form, then I see over the reals it is of this shape. So there's 2 positive eigenvalues and 1 negative. If I look at the complexification and then projectivize it, then I get a projective plane inside this 21-dimensional projective space we had when describing the period domain in general. And here we had the smooth quadric and its intersection with this plane we call QD, so the Dwork quadric. So this is still a smooth quadric. Because the intersection form here is non-degenerate. The period domain D here intersected with QD, the Dwork quadric, is then the Dwork period domain. This turns out, so that now there's a real condition, this turns out that this has 2 connected components. If you write elements in this period domain as A sigma plus B sigma bar plus C L C times the Dwork line bundle, then the real condition becomes A squared plus B squared is bigger than 2C squared, where we assume that we normalize the holomorphic 2 form such that the product is just 1. So then we can restrict the universal family over the whole period domain to the Dwork period domain, and this is almost the Dwork family, not quite, because there's a natural action of some finite index subgroup of the orthogonal group of the original lattice. And this then is roughly A1, or rather the curve C I introduced before. So this then gives the Dwark family, so this descends to the Dwark family S over A1. So the image, the picture for the twistor family is similar. Here the transcendental lattice is extended by the twistor line bundle, which was just the hyperplane line bundle. The intersection form is diagonal again, but now with all eigenvalues positive. Again, we can look at the associated projective plane, which sits inside our P21. There is the smooth quadric that intersected with P2 is still a smooth quadric. We call it the twistor quadric, smooth quadric. And the twistor period, the period domain here gives the twistor period domain in here. And for smooth quadric, it turns out, for this intersection form here, it turns out that this thing here is in fact the whole projective smooth quadric, dt. Okay, so and then the restriction of the universal family gives us the twistor family. The quadric is of course isomorphic to P1, and this is the twistor space. This is the twistor family associated to this line bundle LT. And finally, the Brouwer picture here. I think by now you guessed the idea is we extend the transcendental lattice by the Brouwer line bundle. This was the line bundle of the fiber. This now is for the first time is a real three-dimensional space with a degenerate quadratic form. In particular, when I now intersect the period domain with the associated projective plane, so this would be the Brouwer period domain. This is something singular. It corresponds to the union of two P1s. Okay. If you're interested in the period domain itself, so the restriction to this projective plane here gives us the Brouwer period domain. This is again the union of these two P1s, where now I take out the intersection point of these two lines, and the restriction of the universal family of Mark cathedras now gives us, let's say, to one of those lines minus the intersection point, gives us the Brouwer family. And for the twistor family, neither for the twistor family nor the Brouwer family, I can take a further quotient, as I can in the Dwark pencil. So these two constructions are complex. I cannot make them more algebraic. They won't be any more algebraic than what they are. For the Dwark family, it's slightly different. And maybe I finish by drawing pictures for these three families once again. Let me do this. Let me try several things. So here I drew the twistor base, the base of the twistor family, which was a sphere. We can think of this as S2 or P1. Then there was the point that corresponded to the original K3 surface S, which I drew as a north pole, and then the south pole would be a sigma bar. Then there was the equator S1, which we had to take out of the Noether-Lefschetz and the CM locus. The Brouwer picture consists of two lines, so just two C's. So there's a C here and the C here. They're distinguished by, it's almost not visible, by the fact that one contains sigma and the other one contains sigma bar. And then there's a corresponding picture for the dwarf family. And you see the condition that the square is positive, of course, specializes to the condition that the square is negative, and then deforms further the condition that the square of the line bundle is negative. In the process, this equator S1 shrinks to the point, intersection point of the two lines. So this would correspond to the infinity in the Brouwer family, for which I don't know any further geometric interpretation yet. Maybe the two-dimensional picture is more appropriate. So then I would split the sphere in the northern hemisphere and the southern hemisphere plus the equator. The northern hemisphere would specialize to the plane C that contains the sigma. The southern hemisphere would specialize to the sphere, to the complex plane containing sigma bar. And the S1 would shrink to the intersection points of the two lines. And on the dwarf side, I would have two hyperbolic planes, the upper half plane and the lower half plane. And the real line separating the two plus a point at infinity will correspond to the equator in the twistor family. And now my hope is, and I have nothing to report yet, is that the Brouwer family, which is one of the three families I understand best, will teach us something about this phenomenon that the real anamorphism fields of the two of any CM fiber in the twistor family is the same as the real anamorphism field of the original K3 surface, and that will tell us how to transport cycles on products of K3 surfaces, one K3 surface, not continuously but like jump-wise from one K3 surface to another in the family given by the twistor space. Okay, I stop here. Thank you very much.